Okay, so welcome everybody to the Institute Seminar Day. Our first speaker is Soumya Dey, and he's going to talk about some elements of big mapping class groups.
Yeah, thanks a lot for the opportunity. So today I'll be talking about some basics of theory of mapping class groups, and towards the end maybe I'll talk about something which I'm currently doing. So the plan of the talk is as follows. So the first thing I'll be discussing is the definition of a mapping class group. Then I'll be defining what is a Teichmüller space of a surface. Afterwards, I will be talking about the action of the mapping class group on the Teichmüller space. Then I'll be talking about what are called surfaces of infinite type and the associated big mapping class groups. Towards the end, I'll be talking about a metric on the Teichmüller space, which is called the Differential metric, DFN. And in the very end, I'll be talking about my current ongoing work with Dr. Gianluca Faraco, who is a postdoc at IISc Bangalore, the zipping map and its action. Okay, let's start. So, what is a surface? For me, a surface is a two-dimensional manifold, possibly with boundary. The examples that come to my mind for the first time is like the plane R2, okay, the complex plane maybe, the closed unit disk in complex plane, say D2, is a surface with a boundary component. A punctured disk, okay, if you remove a point from the disk, a cylinder, Mobius band, etc. So these are some examples of surfaces we'll be dealing with. So it's a classical theorem that says that a closed connected oriented surface is homeomorphic to exactly one of the following surfaces, namely a sphere, a torus, or a connected sum of finitely many tori. So we have some pictures here. The first one, this surface is a very well-known sphere. This is our torus. The third surface is a genus 2 surface. Okay, there are two holes, and this surface can be constructed by somehow connecting or taking the connected sum of two torus. Okay, same for the last one. So you can have a connected sum of 3 torus, and you get this surface. It's a genus 3 surface. So likewise, we can add any number of torus, and you have different closed oriented connected surfaces. Okay, great. So how do we, what do we do with these surfaces? The first object that we will be dealing with is called the homeomorphisms of this S. So for a surface S, you say homeo plus of S is the set of orientation preserving self homeomorphisms of S. Okay, so you consider all homeomorphisms from S to S. So what is homeomorphism? It's a continuous map with continuous inverse, and it should be bijective. Okay, so you consider all such maps orientation preserving from S to S. You call that set to be homeo plus of S. Now, given such a function space, you can always take composition of maps, and under this composition, which is a binary operation, in our case, it forms a group. So homeo plus S has a group structure. It has a subgroup which is homeo 0 of S. What is that? So you consider all F in homeo plus, which are isotopic to the identity map. Okay, and it can be checked that this is actually a normal subgroup of homeo plus. So there is something to be so something that we need to discuss here is if the surface S has some boundary components. In that case, when you consider the homeomorphism group, you only consider those homeomorphisms that fix the boundary points pointwise. Okay, you do not move any boundary point while taking these homeomorphisms. So basically, we consider instead of homeo plus, we consider this. So homeo plus S comma del S. Okay, and also when you have these consider these isotopies, these are also like fixing the boundary pointwise. Okay, I guess the definitions are clear now. So what is a mapping class group now? You have homeo plus and you have homeo 0, which is a normal.
Soumya, can I ask a question? If that is allowed, I can wait until the end. If that's whatever the.
No, sure.
Isn't it necessary for a homeomorphism to take the boundary to boundary?
Right.
But so why are you putting as an extra condition? I mean, homeo plus of S, doesn't it map delta S to delta S?
No, I need them fixed pointwise.
Oh,
it may move the.
Okay. Now got it. Pointwise fixed. Okay.
Right.
Thanks. Yeah, that clears it.
Yeah.
Thanks.
Yeah. Right.
Okay. Thanks.
Thanks for the question. So now what is a mapping class group of the surface? You have homeo plus of S and you have a normal subgroup homeo 0. You can talk about, right? So this quotient group is called the mapping class group of the surface S. Now, what are some basic examples? To start with, you have sphere S2. The mapping class group of S2 is basically the identity group. You don't have any non-trivial element. The same for any disk. Okay, the open, the closed unit disk. For that also the mapping class group is trivial. For the torus, okay, genus 1 surface, the mapping class group is isomorphic to SL2Z. Okay, so this comes from the action of the mapping class group on its first integral homology. All right. So the third example would be something called braid group. You take the closed unit disk and you remove finitely many points. So n number of points, P1, P2, Pn from the interior. And the mapping class group of this space would be the braid group on n generators. All right.
Soumya,
So now,
so
for any,
I have. Could you, since it's an important thing, can we just clarify once again what the right-hand side is in this definition mod of S? Just repeat the definitions, please.
Yeah. So it's a quotient group. You have a homeo plus of S, which is a group, and you have homeo 0 of S, which is a normal subgroup of homeo plus. So you are basically quotienting this as groups.
And homeo plus S was orientation. Could you just say the whole thing once again?
Yeah, homeo plus of S is the orientation preserving self homeomorphisms of S, and homeo 0 of S is all the maps in homeo plus which are isotopic to the identity map. Okay. So basically,
if things have a boundary, then both require all the boundaries to be fixed pointwise. Is that
exactly? If you have some boundary components, homeo plus and homeo 0 both will preserve, the elements will preserve the boundary components pointwise.
Thank you.
Is it okay?
Thank you.
So yeah, so this mapping class group is a very interesting group. Okay, it's quite a big group, in fact. So it's an interesting question to have a generating set for this group, and many mathematicians have tried in the past to come up with some finite generating sets, and the last the most minimal set of generators were given by Humphreys, and so he gives us a finite number of curves on our surface. For any closed surface, you have finitely many curves, and there is something called den twist, which I'll be defining just now. If you take the den twist along those finitely many curves on your surface, those den twists will generate your mapping class group. Okay, so these are elements of your mapping class group, den twists. So let me define what is a den twist along a curve. So let me start with some surface. So for simplicity, I have considered a genus 2 surface, and this red curve I'm calling alpha. Okay, now I'm trying to define what is a den twist along this curve alpha. Okay, so for that, what we do, you cut open this curve. Okay, so you cut the surface along this curve alpha. So you have something like this. Now you have surface with boundary which looks like this, right? You have cut the surface along this curve, red curve alpha. Okay, now what you do, you rotate one of the circles, one of the boundary components by an angle 2 pi or 360 degree. Okay, so now how do you see this action? So the action can be seen by the green curve. Okay, so I have drawn one green curve, or what I am calling is a beta. Okay, so if you rotate the left circle, red circle, by an angle 360, you see on the right hand side you will get this something like this. So the image of the green curve will be something like this. It will have a rotation. Okay, and in the final step, what you will do, you will again glue back the red circles to get finally your final surface. So what is the difference between these two surfaces? There is no difference actually. So as surfaces, this is a self homeomorphism. Basically, along a neighborhood of your alpha, this curve, there is some non-trivial dynamics going on. Okay, so such a map from S to S is called a den twist along this curve alpha, and this can be defined for any simple closed curve on your surface. Okay, so I'm not going to define explicitly what is the map. Okay, but I mean, I'm just giving you an pictorial representation of what is going on. So so this theorem says that you have finitely many curves on any closed surface. If you consider the den twists along these curves, these will be homeomorphisms. And now for each homeomorphism, you have this sits in a mapping class, right? So these finitely many mapping classes corresponding to these den twists will generate your whole group mapping class. Okay, by generating I mean any element of the mapping class can be written as a product of these finitely many den twists. Great. So now I'll be defining what is called a hyperbolic surface.
For genus 2,
so till now,
you're saying that
Sorry? Sorry?
No, I was wondering for genus 2, how many curves are there for how many curves do you take gain with respect to for genus 2?
Oh, so for genus 2, I'll be needing 4 curves. 1, 2, 3, 4, 5. 5 curves I need. Maybe towards the end I can give one such set of curves, which I mean the den twists that generate the whole group. Okay.
How many generators does the braid group have? Oh, okay. Oh, these are just.
Am I? Okay. Is my audio freezing sometimes?
No.
Okay. So what is a hyperbolic structure on your surface S? So for a topological surface, if you have some charts, the way you define a manifold. In this case, we have on the right our hyperbolic plane H2, and you have some charts. So you have some neighborhoods that cover your surface, and from each of these neighborhoods you have homeomorphisms that take you to the hyperbolic plane, and the transition maps are isometries of H2. So basically Mobius transformations. So if you have such an atlas on your surface, you say that this is a hyperbolic structure. Now, let me define what is the Teichmüller space corresponding to a surface. A marked hyperbolic structure on S is a pair x, f, where f is a homeomorphism from S to x, which is called a marking, and x is a hyperbolic surface. Okay. So for a hyperbolic surface x, if you take such a marking, the pair x, f is called a marked hyperbolic structure on your surface S. Now you define two such marked hyperbolic structures, xf and yg, to be equivalent if there is an isometry phi from x to y such that phi composed f is homotopic to g. Okay, and now you consider all these equivalence classes of marked hyperbolic structures. This would give us the Teichmüller space corresponding to S. We denote it by Ts. Now, how do you actually come up with such hyperbolic surfaces? Actually, let me say. So by uniformization theorem, any surface with having Euler characteristic negative can have a hyperbolic structure. So for simplicity, we will be dealing with closed surfaces here. You take some SG, which is a genus G surface for G greater than or equal to 2. So I'll give an algorithm to get a hyperbolic structure on this surface SG. So what we'll do is, you start with your surface. Again, I'm doing this for a genus 2 surface. So this is your genus 2 surface, and now you have these red curves. Okay, if you cut along these red curves, what you get is a set of pair of pans. Okay, so each of these components will be like pairs of pans, and now if you cut along these blue curves in your pairs of pans, what you will get is two pairs of hexagons. Okay, and there is a way to get hexagons in your hyperbolic plane. Okay, so there is a theorem that says that given 3 positive real numbers, you can have up to isometry, you can have a unique right-angled hexagon in your hyperbolic plane with having these 3 lengths to be your alternate sides. So what we can do is we can have any 3 positive real numbers, say L1, L2, L3, and you can have hyperbolic right-angled hexagons in your H2 with having these red lengths or arcs having lengths as L1, L2, L3, and this will give you a hyperbolic structure on each of these hexagons. Okay, and you can glue them back to get hyperbolic pairs of pans, and then again you glue back to get your hyperbolic surface. Okay, so what I'm telling is it's not very easy to see. There are many things to be checked here, but this is the recipe. Okay, so in this way you can give a hyperbolic structure on any closed genus G surface with G greater than or equal to 2. And while this gluing process, there are some parameters, okay, and that can be varied. For example, these 3 length parameters, you have the freedom to choose any 3 positive real numbers for these 3 lengths. And also, while gluing, you can have some twist parameters. So I'm not going into all those details, but in the end, you have some 6G minus 6 many parameters, real parameters, for each point in your Teichmüller space. So for each point in this R, so this Euclidean space, basically, you have a point in the Teichmüller space of SG, and these are called Fenchel-Nielsen coordinates. Okay. Now let me go about defining what is the action of the mapping class group on your Teichmüller space. Okay. So mod S acts on Teichmüller space as follows. For any point phi in mod S, what you do, you define this. So phi dot x comma f is x comma f composed P inverse, where P is an element in your phi. Okay, so this is the action, and now you can this can be proved that this action is actually properly discontinuous. Okay, so this is the definition of proper discontinuity. So for any locally compact space X, the action G on X is properly discontinuous if this intersection, so all G such that GK intersection K is non-empty, this set is finite for all compacts. Okay, so this can be shown that the action of mapping class group on Teichmüller space of a finite genus surface is properly discontinuous. Now let's come to the surfaces of infinite type. So till now we were dealing with all surfaces which have finitely many genus and finitely many boundary components and punctures, etc. But there can be surfaces where number of genus is infinite, or say the number of punctures or boundary components, these are all infinitely many. For example, so the first example you can see here, you have a surface with infinitely many genus, and this is like open in one end. Towards the above, it goes on, right? So this is called the Loch Ness monster surface. The second example is open in two ends. Okay, so in both the above and below, it has infinitely many genus. And in the third example, it's like a tree or binary tree, right? And in each of these directions, okay, you have infinitely many genus. So any kind of this kind of things can happen in surfaces of infinite type. So now, how do you define the type? Okay, a surface S is of infinite type if the fundamental group of S is not finitely generated. Okay, so now we will be dealing with all those surfaces which have pi1 as not finitely generated. Okay, and any such surface has a mapping class group associated with it. The same definition works here, and these are called big mapping class groups. Now you can ask, why big? Why are we saying these are big? Okay, so let me give some reason why am I calling these surfaces, these mapping class groups, to be big. So let us come to the first theorem here. So for any infinite type surface S, mod S is actually uncountable. Okay, and in fact mod S is a Polish group, which is not a Lie group, but it's a Polish group which is homeomorphic to the Bearer space n to the n, all functions from n to n. So it's quite a big group. Not only that, there is a theorem by Augab, Patel, and Flamis in their recent paper in 2020. So if S is an orientable infinite genus surface with no planar end. So for example, the surfaces that we have given in the previous slide, all these have. So I'll not be defining what are planar ends. So in these examples, mod S contain an isomorphic copy of every finite group. So this is quite mysterious and interesting to me, that any finite group can be embedded in any such mapping class group. And in addition to the above thing, if the end space, I'm not going to define what is the end space. So if end space is self-similar, then the mapping class group also contain an isomorphic copy of every countable group. Okay, so this is a big result actually. So any countable group can be embedded in one of these, each of these type of big mapping class groups. Okay, so let me go over to the last section of my talk, which I'll be talking about an ongoing work with Gianluca Faraco. So we have defined some element in the mapping class group of a flower surface of 3 ends. So basically this is our surface. So in ladder surface you have 2 ends. So one goes in the above and one in below. In this case you have 3 directions where you have infinitely many genus. Okay. So in these 3 directions you have infinitely many genus. Now for such a surface which we call FL3, or the flower surface with 3 ends, we have defined some map which we are calling zipping map. So what is the map? Let me just define it. So you can have these curves which I am calling this A0, starting with A0, A1, A2, AN in the above, and A minus 1, A minus 2, A minus 3, like this below. So this family, on this family, I'm going to define. So if we can define in each of these blocks this map, we can extend this to the whole of FL3. So what I'm doing is I'm sending AI to the curve AI minus 2. Okay, so this AI here goes to A minus 2 here. So it's kind of the whole surface is moving towards below. Okay, it's kind of a you're basically trying to zip in this direction. So if you have a zip in this part, you are basically moving it upwards. Okay, so for such a zipping map, we have shown something. So let me define what is a Fenchel-Nielsen metric. This will be needed to say what we have done. So for any surface or infinite type surface S, if you have some pan decomposition, so like we have defined what a pan curve while defining hyperbolic structures. If you have such a pan decomposition of your surface, let's say Ci, given 2 elements in your Teichmüller space, say H1, what I'm calling is like x comma f, and H2, which is y comma g, we can define a distance between two such points on your Teichmüller space, and the definition is like this. Okay, so you have some LH1 of Ci and LH2 of Ci. So basically these are lengths. So LH1 of Ci is the length of Ci in the metric or the Teichmüller space H1, and the LH2 of Ci is basically you are taking the length of Ci in the structure H2. Okay, and you're basically taking the quotient and taking log, and in the other part you are also comparing something like LH1 Ci, theta H1 Ci, and LH2 Ci and theta H2 Ci. These thetas are twist parameters. In our case, I will be taking these as 0, but this is a general definition. So such a if you have such a definition of a metric, you can define what is this called a metric on the reduced Teichmüller space. So this supremum over maximum, this is not always finite. So you have to start with some fixed H0 in your Teichmüller space, and you consider all your points which are in finite distance from your H0. If you do that, then you get some subspace of your Teichmüller space which is basically bounded, or any 2 points are in bounded distance. Okay, so this is the Fenchel-Nielsen metric. And now for our work, what we have done is we have our zipping map as we defined. Now we are starting with some structure H. Okay, so what is this H? So H is basically, we have all these curves, and these curves will give you some band decomposition, and any band decomposition is actually giving you a hyperbolic structure on your surface. Okay, I'm taking I'm telling you a lot of things which needs to be discussed in detail, of course, but what I'm trying to say is you have some set of curves on your surface, and if you define the lengths of these curves, you will get a point in your Teichmüller space. Basically, you fix a structure by giving the lengths of these curves. Okay, so what I'm doing is, you give this red curve on your surface. Okay, here is the red curve. You say that this red curve has length 2, and all other green curves has length 1. Okay, so this will induce a hyperbolic structure on FL3, and you apply your zip map on this point of your Teichmüller space, and you consider the orbit under iterations of zip. So this will give you an infinite subset of your Teichmüller space. Not only that, we have shown that in this Fenchel-Nielsen metric, this is actually sitting inside a ball or closed ball of radius log 2 around our structure H. And not only that, we have shown that this set of infinite points in that closed ball doesn't have a limit point. Okay, so it's a bounded infinite set, but it does not have a limit point. And this kind of phenomena is called bounded regeneration. So this is somehow the first time something like that, some such example has been shown. And one consequence of this fact would be that this Teichmüller space or Fenchel-Nielsen Teichmüller space is not a proper metric. So these are some references, and if there is some time, I don't think there is time.
Maybe we'll come back to questions after Aparna's talk if people are still
Sure.
interested in hanging out.
Thanks a lot.
Thanks a lot. Very interesting talk.